The next speaker is Dan Stowell from Naturalis, and he will, I think, answer a few questions for Axel. And he is going to tell us about how deep learning can tell us something about Orthoptera sound classification.
Yes, thank you very much. Yes, I'm very pleased to be here, and I'm pleased to be speaking after Bodewijn, especially because I'm using his data and very grateful for it. I work at Naturalis here. I also work at Tilburg University, and I'm going to be speaking today about a project which is the MSc thesis of Dario Gandini, who was working with me last year. I work on sound recognition. I've done a lot of work on bird song recognition, and so actually especially related to the question Axel was asking. We have a lot of progress in machine learning for biodiversity sound surveying. And one of the things that happened in the bird song world is pretty much that these large data sets were created, and that was one of the main forces that led to the possibility of good quality machine learning sound recognition for birds. So I'm motivated to improve the technology for these things and also to use them for biodiversity sound surveying and also for understanding acoustic behavior. So of course Orthopterans are a really interesting case to be working on. In a lot of sound analysis and a lot of different domains, and in machine learning for sound analysis as well, we do often use the spectrogram representation. So you see here we've got, so in the lower left, we've got a dawn chorus of many birds singing in the morning. And you can see on the spectrogram or sonogram representation, even if you don't understand what is there, you can see that there is a lot of structure to it. And this is actually a bit of a clue that this representation is good for birdsong automatic recognition. We can see separate units of vocalizations from different individuals, different types of sound that might be indicative of species. You may be familiar with looking at these things for orthopterans and other insects. We can, as Bodewijn said, we can use this to look at frequency ranges, but often there is less detail than we might see for a birdsong sound scene. So we want to use deep learning, especially for biodiversity sound monitoring. I should say, actually, part of the motivation for using deep learning is that it is, well, we know that it's very powerful in a lot of different domains. It should be quite a flexible way to do noise-robust sound surveying in a lot of different contexts. So that's why we use that particular paradigm. What makes it succeed is, firstly, large labeled data sets. So this is less about the actual algorithmic technology and more about the availability of the data. This is really an important thing. This is true for speech technology, birdsong recognition. It's going to be true for insect and orthopteran sound recognition as well. Now, what has been something of the revolution in speech technology as well as birdsong and related sounds is that we can use this spectrogram directly as the input data. So you may be familiar with machine learning technologies where we input features such as the frequency range or the rate of repetition as features into machine learning. Part of the strength of modern techniques is that we take the almost raw data, these sonogram representations, directly as the input. And so the main tool of progress for that is that a convolutional neural network, that's what I'm going to be using in this talk, a convolutional neural network is able to digest this spectrogram data directly. So we want to apply this to orthopterans. It's an interesting challenge, certainly, I would say so. It's also important because I don't need to explain to you why orthopterans are important here, but certainly for biodiversity monitoring applications as well. There is very little machine learning research on it for various reasons, but as we've seen certainly in the birdsong community, an important part of it is just that the data sets need to be sort of put in place, and then machine learning researchers will come along and have a go at it. I want to take you through a little bit of the previous literature just to show you some ideas that I think are interesting. There is a nice paper from 2007 by Ganchev and Potamitis in which they studied quite a large number of insects within a classification method. And their approach was to use the spectrograms and to derive features from them. And they would sort of recreate the taxonomic hierarchy with a separate classifier at each point in this branch. So you can imagine a little network of classifiers where one classifier passes it down the tree to a different classifier. So this is a good way to sort of divide and conquer the problem, but it's also, it's not exactly the way we would do it these days, but it's certainly an interesting prior work. More recently, Inish Nolasco, who's within my group, she applied deep learning to, this is beehives, so the actual ensemble beehive sound recording to detect sort of activation of the queen. And so we demonstrate that it's possible, but the methodology needs work. So it's not that you can take, let's say, a speech recognizer or a birdsong recognizer, apply it directly to insect sounds and immediately get good performance. We do need to work on the methodology a little bit. And one piece of inspiration, I'm going to go back to 2001, by a paper by David Chesmore, who has quite a nice, thoughtful paper about the way that insect sound are produced. Of course, they are produced differently than us vertebrates. With birds and mammals, for example, we often produce sound inside the body and then it's filtered through our vocal tract. And that's why the spectrogram representation is quite useful, because then we get these resonances, which are a useful part of the analysis. But because orthopterans and other insects are producing sound a little bit more directly produced with the air, as David argues, you can look at literally the shape of the waveform, so that's the pressure wave being produced. And in his paper, he took features directly from the shape of the waveform. And it's quite an interesting paper. It's, of course, a little bit old now in machine learning terms, but still interesting. Now, so he was advocating using information from the raw waveform. And there is a really nice, timely connection here, because deep learning, as I said, for sound, we typically analyze spectrogram data, but there is a move towards using raw waveform data. So starting from the principle that we take the waveform and we apply a Fourier transform, well, a lot of Fourier transforms to produce spectrograms, there is this pre-processing which we're doing by applying our own beliefs about what is a good pre-processing of the data. But increasingly, there is an interest in going from what we have on the left side here, so extract a spectrogram and then put that through the different layers of the deep learning method, to the right-hand side, where we expect that we can train a deep learning system to extract its own features from the waveform. So whether or not that is going to be a similar thing to the spectrogram, that's essentially, we don't worry about that, we let the deep learning system learn for itself. And as we've discussed, spectrograms are more appropriate for mammalian sound, but even with mammalian sounds, such as speech, music, other things, there has been a lot of useful, positive results that you can, with enough data, you can train a deep learning system to learn things directly from the waveform. So we're now at this position where the deep learning technology, in a sense, is ready for orthopterans. So, very kindly, we have this data set which Baudouin Audet has allowed us to use. So I think this is a subset of what will be on Sino Canto, at least has a lot of overlap with it. Yeah. And so in this study, we have 9 different species. We need to use species for which we have many examples of the same species in order to train and then test the algorithm. And so we have these 9 species here, and the number of recordings and the average duration listed there. So one of the things that we did in this is to standardize the recordings to 44 kilohertz. This is something that I think will come up when we think about applying machine learning to Orthopteran bioacoustics in future, because of course these different species make sounds with different bandwidths. Some are quite ultrasonic and some are not. But in order to process them all through the same system, if you imagine your automatic monitoring, you just choose your sound resolution and then leave it running. You don't choose it according to the species that arrives later. So we chose 44 kilohertz, CD quality, relatively standard. And if we look at that with the Gryllus campestris here, okay, so most of the energy from the Gryllus campestris is indeed contained within the audible domain there. So here we've got a full bandwidth recording, and then I've artificially limited it to 44 kilohertz. So you can see most of the energy is still there, and we can still see a pattern in the spectrogram, so we can still be confident that there is information there. But still, there is something lost. There is still information which certainly, I would say, is going to be useful for an automatic recognition system. That's something for later, because in this study, we're using the 44 kilohertz representation. You can see from the waveform as well that most of the energy is preserved, so the overall shape of the waveform is still very similar. So what I have on the screen here is the sort of deep learning architectures that we use. You don't necessarily need to understand these diagrams, but I'll just tell you we are comparing 3 different deep learning architectures. We start with, the first one is a baseline system, which is a quite standard off-the-shelf convolutional neural network. So this is our number one, the baseline. Part of the issue here that we're studying is to be able to perform machine learning with relatively small data sets, because although the data set is fantastic, it is much, much smaller than is typically used for speech recognition or other contexts. So one of the things we can do about that is to pre-train the network. So we can take a network, and instead of training it directly on the Orthoptera recordings, we first train it to recognize a lot of generic sound scenes. We take a standard big data set from Google, which is called Audioset. This is from YouTube. It has birthday parties, basketball, dogs, cats, all kinds of things. And that's a sort of generic classification task. We first train the system to handle this generic task, and then in a second phase we train it to recognize the orthopterans, with the presumption that in the first phase it has learnt something about sound generally. So that's number 2. Number 3 is where we're doing the raw waveform work. Now we're using a previously published raw waveform algorithm. And in this image here, you can see we've got the raw waveform. This goes in, and these first steps of processing are kind of the feature extraction. So the deep learning system will learn to do something which might be like a spectrogram extraction or might be something different. And then the final layers, the final steps of processing are similar to what we have in the other algorithms. And I'm going to add one more dimension to the comparison. One of the standard things that is done in deep learning quite commonly is to augment the data set, which means to artificially expand it. So in this case, we have a couple of hundred sound recordings, and it's almost certainly not enough to train a deep learning system. But even when you have a large data set, to improve the quality of deep learning, you can artificially expand the data set by taking each one of your sound recordings and manipulate it somewhat. So you add some noise, or you maybe move the audio in time, or maybe even change the frequency of the audio. So you make small modifications to the sound to create an artificial extra training example. So you do that lots. You can increase the size of the data set by 10-fold, by 100-fold, and that's a very common thing that is done in a lot of deep learning applications. And it should be very useful here because we have relatively small data sizes. here are the results then. So what we have, the confusion matrix there shows you what is the, for the best performing system, we simply have pretty good performance. We have a good classification across all of them. And in the table you can see various different accuracy results for the different configurations. You can see by comparing the left column and the right column that this data augmentation that I just talked about is always useful. So we're expanding the data set from something like, well, from 158 files to 1,422, approximately 10 times the size, and it always helps. Now, the baseline system with the data augmentation actually turned out to be the best performing system in this pilot study. The pre-training, this second row, wasn't particularly helpful. I think this for me is quite an interesting finding because, as we know, Orthopteran sound is quite a unique category, and I've argued in this talk that there are some special aspects to it, which I think, contrary to what machine learning researchers might often think, pre-training a system on birthday parties and cats and dogs seems, at least from this evidence, not to be a good way to get it ready for learning about Orthoptera. Now, the raw waveform system, that performed worse than the other systems. That's actually to be expected because it's hard to train these systems. We've got this extra part of the job for the system to learn. So it has to learn not just about how to make the later decisions, but also what sort of information to extract. So we expect it to perform worse. But the raw waveform system is something that is going to be the basis of future work. I think as we go forward, that will be the basis of what we use. And what's very encouraging is that even with this relatively small amount of data and this relatively small amount of data augmentation, 72% performance, okay, we're not going to deploy that in the wild just yet, but it's a really encouraging start. So, to summarize these tentative conclusions, data augmentation always helps. Pre-training from general purpose audio is not, in this case, the thing to do. And raw waveform recognition is feasible, but it's harder to train. Dario's code is available there for anyone who should want to rerun or expand on those methods. I want to finish with a sort of looking forward. So we are already building on this initial work, and we want to do more in this domain. So you heard already that Sino-Canto is a database which is going to be a great resource for sharing and crowdsourcing of Orthoptera recordings. As well as Baudouin, I would certainly encourage you to contribute data sound recordings to Sino-Canto under open licenses. One of the things that I will say from a machine learning point of view is that you do want clean studio recordings and you want terrible, noisy field recordings. We want to represent all of the kind of sonic variety within which you will encounter different Orthoptera species. So don't be worried about having a moped in the background or something like that. I think all of these sound recordings, from my perspective at least, will be useful. Yeah, and so the future work, of course, is to expand it with more species, more recordings, and more contexts. I have there a table of different data sets going across Orthoptera and other insect species. I think generalizing across multiple related tasks is another topic of interest. And yes, so we're working on some extra deep learning methods that might help even more with this, and I can talk about that later if anyone's particularly interested in that. But otherwise, thank you very much.
Okay, thank you. I can imagine that there are many questions, but we don't have time for that.
Ah, I'm sorry.
Sorry, Dragan.